Hello guys. In the last video we have had in the last couple of videos I would say that we have had the introduction of oscillations. Okay. Now in this video we are going to discuss about the differential equation of simple harmonic motion. Now I never mentioned this in the last videos, this topic called simple harmonic motion, but then what is it? Let us understand. We had this spring here, this rigid support, and then this spring here, and some mass attached to it, and I just gave it some displacement x here, and the restoring force was F, and that was towards the equilibrium position of the spring. Okay, and when I gave it some initial displacement and I left it over there, what happened? The restoring force pulled it back towards the mean position or the equilibrium position, and it continued to move further, thus compressing the spring. Okay, and then again, while the spring got compressed, the spring was again pushing the mass back to the equilibrium position. So here the restoring force, okay, the force acting on the mass was always, it was always acting opposite to the direction of displacement, and it was proportional to the displacement. Correct. This kind of motion, it is called simple harmonic motion. I'll just write it down over here. Simple harmonic motion, it is, I'll write short form of that, SHM. It is the motion, or rather I would say it is the to and fro motion of a body in which the force is always proportional to the displacement and acts opposite to it. But when I say opposite to it, it means opposite to displacement. So what we have is F is equal to minus k into x. Correct. Now that is simple harmonic motion, definition of simple harmonic motion. So we'll take this thread and move further. Okay. Now mass of this block is m, correct, and the force acting is F. Now what does Newton's second law tell us? Newton's second law tells me F is equal to m into a, force is equal to mass into acceleration, correct. And what does this oscillation equation tell me? It says F is equal to minus k into x. Can I equate both? I can do that. Okay, and so I would say that m into a is equal to minus k into x. Okay, so if I take this a here and I take this m down there on the right hand side, it would be minus k upon m into x. Correct. Now what is k? Is it not the spring constant or force constant of the spring? Correct. So k is constant for the system. Correct. What about mass? Because of application of this force, or because of the displacement towards right, is the mass going to change? It is not going to change, right? So even mass is constant for the system. So mass and k, if they are constant, can I say that acceleration is proportional to displacement and acting in the opposite direction? Correct. So we can say that. And then this is simple harmonic motion, correct. So what does it mean? Simple harmonic motion is the motion where the acceleration of particle is directly proportional to its displacement and acts in a direction which is opposite to that of displacement. Okay, and this acceleration is always going to be acting towards the main position, correct? So when the mass moves towards right, the spring is in extension, the force will or acceleration will act back towards the main position. When the mass compresses the spring, again the acceleration is going to be back towards the main position, so towards the right, isn't it? So this is going to always be the case in simple harmonic motion or this oscillatory motion. Okay, but then when I started talking in this video, I had said differential equation. Now where is differential? I can see only force here and mass and acceleration and force constant and displacement, right? Nothing called differential or differentiation of any quantity. But then yes, I have my acceleration here, isn't it? Now what is acceleration? Acceleration is my rate of change of velocity or time rate of change of velocity. What about my velocity? Velocity is time rate of change of displacement, and yes, I have displacement here. I have this displacement x towards right, or then once it comes back to the main position and goes back compressing the spring, again the displacement is going to be x, isn't it? Displacement is there is some time interval in which this displacement is changing, correct? Displacement is changing. Now when it is here, the displacement is 0. When it is here, it is something or some positive changes, some more positive, some more positive, some more positive, and some more positive, maximum here, correct? And then it will go on decreasing, it will come to this, and then again it will increase towards left, so it increases on the negative side, correct? So displacement is changing, it is function of time, correct? So there is every reason for us to make use of velocity and acceleration, isn't it? So if x is my displacement, then my velocity is equal to dx by dt, and my acceleration is equal to dv by dt, and dv by dt is nothing but d dt of dx by dt, correct? So my velocity is my first derivative of displacement. But then what about acceleration? Is it not second derivative of displacement, or it is first derivative of velocity and second derivative of displacement? So I call it d2x by dt square. I call it d2x by dt square. Some people call it d square x by dt square, but then it is not d square x by dt square. It is not squaring something, okay? It is a second derivative. It is a derivative of velocity or then second derivative of displacement. So we should call it d2x by dt square. So now if I put this d2x by dt square here, what do I get? I get that d2x by dt square is equal to minus k by m into x, or I take this on that side, d2x by dt square plus k upon m into x is equal to 0, or then I can also write this as m into d2x by dt square plus kx is equal to 0. Now here, I differentiate my displacement, I get velocity. I differentiate my velocity, I get acceleration. So this quantity, this is expressed in some differential form, some differentiated form, right? That is the reason why these equations 1 and 2 and 3, they are called differential equations of SHM or differential equations of simple harmonic motion. Now you would say, why these three forms? Okay, there is no specific reason for that. Okay, but then once you have this equation or this, okay, you can determine the position at any instant, or then you can determine the velocity at some instant, some time instant, or velocity at some particular displacement. You can even determine the acceleration at some particular instant, correct? Now from this expression, what do you make out? My acceleration is equal to minus k upon m into x. And what is this x? X is the displacement from the mean position. X is the displacement from the mean position. You have to keep this in mind. Okay. Now, suppose you put x is equal to 0. When you are putting x equal to 0, what does it mean? It means that yes, I am here. I am not going anywhere. So when I am at the mean position, my acceleration is equal to 0. When my x is equal to 0, my acceleration is equal to 0. Okay. What about moving the maximum distance towards right or towards left, for that matter? Okay. Over there, my acceleration will be maximum. So when I'm at the extreme position, my acceleration is maximum. Now here we will have to define a few quantities like amplitude or time period, or or maybe wavelength, and all those kind of things there. Okay, we'll be discussing that in the next video, but for now it is differential equation of SHM. Thank you so much.